Welcome everyone. As per the campus tradition, we will start with the Somaiya campus prayer. I request all of you to please rise for the campus prayer. I request Professor Subhash Krishnan, Head Department of Mathematics, to felicitate our speaker for this session, Professor Jyotshana Prajapat.
Thank you, sir.
I invite our speaker for the day to enlighten us with the first session. Thank you.
So firstly, I welcome you all for the Teachers Engagement Workshop, which is funded by NCM. I also welcome the participants who are online. We have more online participants than offline as usual. And I hope that at the end of this workshop, we will be able to learn much more about the subject. We will have a lot of questions and discussion sessions. And yes, one more important thing is today is a festival in the country, and it is a festival which is celebrated in all parts of the country in some form or the other. So greetings from our behalf for the festival. to each and every one of you. And I will begin my lecture now. I do request even online participants to send their questions. If you are not able to answer today, maybe we will be able to take it up in the discussion sessions tomorrow or day after, or at least we will share it with you. Unfortunately, we are not going to telecast the discussion session for the online participants. Do you want to do?
Recording
Okay. We may upload the videos later on of the discussion sessions also. But to begin with, the discussion sessions are not going to be transmitted online. So what I'm going to start with is the first order PD. Before I begin, it is important for me as a student of Mumbai University to remember Professor Vanita Rao, who has done a lot for the undergraduate teachers by organizing series of teachers enrichment workshop. And since some of the undergraduate teachers told me that maybe we should have these activities again, so this is an effort to restart the the tradition which Dvanita madam had started. So wish me luck, and may her blessings be with us. So I'm going to speak about first order PD. Basically, whatever is going to be discussed about the first order PD is certainly part of the undergraduate syllabus, which has been prepared for the undergraduate course of Mumbai University, and with various colleges becoming autonomous, I hope you all will be also able to use it to your advantage. So what is a partial differential equation? So it is a relation given by f of x, y, z. You can have the domain consisting of as many variables as you want. You can have functions. So here I should have written x, y, z, v, x, y, z. So and then you have derivative with respect to ux, uy. You will have ux, x, ux, y, and so on equal to 0. So a partial differential equation is just going to be a relation of this form. In this particular course, we are going to focus on just second order partial differential equation, and at the most function of two variables. So basically the equations that will be considered in this particular course are going to be of the form ux, y. So this is dependent variable ux, uy, uxx, uxy, uyy equal to 0. So this is usual expression of fully nonlinear second order partial differential equation in two independent variables. U is the solution which you are going to look for. So what is so these are the second order. What I have written is second order PDE. As we said, when we are studying ordinary differential equation, we are only solving functions of one variable or first order derivative. As soon as you go to functions of two variable and you want to solve for differential equation, it becomes partial derivatives, hence it is called as partial differential equation. There will be speakers, subsequent speakers today in afternoon, who are going to speak about say heat equation, and also wave equation, and maybe Laplace equation I will do later. I believe they will have lot more motivation to to show it to you all with applications, etc. I'm just going to start with basic first order partial differential equation. So let me start with recalling what you have studied in your ordinary differential equation course, if you remember. An ordinary differential course is ordinary differential equation is just going to be something which is going to involve single derivative, right? So it will be du by dx is equal to 0, or more generally you have studied du by dx is equal to f of x u. This is still a very general representation where I am taking the right hand side to be function of your independent variable, and u is the dependent variable. So this is first order derivative. So you usually require one condition to be able to solve this. So this is you require ux naught to be equal to, say, f of x naught, something like this. So what was this called as, if anyone remembers? This was usually referred to as initial value problem, right? So of course you called it as initial. You are given the value of the function which you are looking for at one point, and then you want to solve. What I would also like to relate is that it is easier to view all these objects as geometric quantities. Let me go to what we all know as curves. So what do you mean by a curve? What do you mean by a curve? Yes? Function of. So it is actually a function which is going to be function of one variable. You can always call it as a curve. So so I will call it from AB to, in fact, we can have it to Rn, right? So though in real life we are going to know only for 2-dimension or space curve. That is what we are going to study. So actually, if you are having a function something like this, so it is going to be a curve. In general, you have what is called as a continuous function from R, or an open interval in R to Rn is a curve. The thing is, we are not just happy with having continuous curve. We want something that is represented by this particular equation to be taken into account, right? How do you determine a curve? You want to talk of the tangent vectors to the curve, right? So once you have, so usually this is going to be a C1 function or piecewise C1 function is called a curve. That is what I am going to say whenever I am saying I am thinking of a curve. It is going to be this. And what we know is that if I am going to talk about curve in u of t, I will write it as xt yt in the simplest form. Then the tangent vector to this curve is given by, yes, derivative. It is given by u prime t, which is x prime t, y prime t. So if you go back to this particular equation, so of course here I have used x as notation. So you consider initial value problem. Du by dt is equal to f of t u. So for simplicity, if I just write u at t naught is equal to u naught, then what does it mean? I am looking for a function which is going to be from, so in neighborhood of T naught, so it will be from T naught minus delta, T naught plus delta to R2 or R3 or Rn. Okay, and what does this give you? This equation says that the tangent vector to this particular curve is equal to f of ut. Okay, so you are given a condition on the tangent vector. So here your right hand side, you can think of it as a vector field. F is a function from, suppose we take it from, f is a function from R2 to R2, or f function from R3 to R3. So this one can think of it as a vector field. Anytime you have a map from R2 to R3 or Rn to Rm, it is called as, one can think of it as a vector field. Why vector field? At every point in your domain, it is assigning a vector, okay, which is given by f of p. At every point p, you have a vector which is given by f of p. So what does this equation say? I am given a vector field, and so u at the point t is going to be a point in your space. It will have coordinates x, t, y, t, and what you are trying to do when you are trying to solve this particular equation, what you are trying to do is that you are trying to find a curve, such that at every point along this curve, the tangent vector corresponds to the value given by the vector field. Okay. So this is what is called as solution to initial value problem, is called as an integral curve. Okay. So this is what many times you all are doing in the real life application also. When people talk about curve fitting and those kind of real life application, you are just solving the ordinary differential equation. The most important result which one studies in ODE is that basic existence and uniqueness theorem, which says that if I have say sufficient regularity condition, say f is C1, you can also assume f is Lipschitz, then there exists unique solution in neighborhood of your initial value. So the existence and uniqueness is guaranteed in neighborhood of your initial value only. You cannot say that I want my solution to exist from this entire interval, from 0 to 1 or entire real line, which would be very nice to have a solution for all points on the real line, right? You can solve for any initial value, but in real life that doesn't happen. The basic existence and uniqueness theorem guarantees that the solution exists. This is the most important theorem which we study in ordinary differential equation, and believe me, you use it very, very frequently for partial differential equation and later on studies also. So so this is integral curve. What are we interested in? We are interested in partial differential equation, right? So I will go back to go to surfaces. Okay. So what do you understand by surfaces? What do you mean by a surface? Yeah. So surface is some object in R3, right? And what does one understand by a surface? Anyone? Please answer. Please feel free to answer.
Something homomorphic to two-dimensional space.
Who is that?
Something homomorphic to a two-dimensional space.
Okay. Online answer. Okay. So something homeomorphic, diffeomorphic to two-dimensional space. Of course, thing is that is a very abstract definition. When you are talking of a surface, we know without the definition also that the top of this thing is a surface, or this one is a surface. So you don't say it is a solid object, right? It is a surface. The top part is a surface. So the standard surfaces which one has studied is going to be cylinder, sphere. You also know cubes, right? So is cube a surface? Is cube a surface? If I draw a cube, is it a surface? It is a surface. It is a surface, except for these points, right? Like these are the corners. So it is not, when you're saying something is a surface, you want to say it is flat. And as one of the participant pointed out, it is just something which looks like a plane. Whenever I say the best surface which everyone will be very happy on to be on is a flat surface, right? But Earth itself is not flat, right? So we are on a spherical surface. It's a solid object, but we are on surface of a sphere. So that is why there is need to study geometry, which is not just Euclidean. You have different geometries which exist. Okay. So coming back to surfaces. For sake of simplicity, I do not, just as you see here, when I look at this curve also, here you see there is a corner. Okay, it looks like a corner, but still what I can do is if I can write a parameterization so that I can walk around this path, then in spite of the fact that there is a crossing over here, I will have a tangent vector at every point, because when I am going from here to here, I will have this tangent vector. When I come back over here, I will have this tangent vector. So this is still a nice curve as long as I am able to write a good parameterization. Okay. Of course, we all know this is your standard example of a function which is continuous but not differentiable, right? So why? Because it has corner, right? So here, that is the advantage of parameterization, that here you see, here whatever you do, you will not have a tangent vector at this particular point, but here it looks like a corner, but I can still, if I am able to write it nicely, I will be able to get a tangent vector. Okay. So same thing over here. Of course, this is not the ideal surface which we are going to be happy to work with, but of course it is still not bad, because at a given time I can just restrict to this flat part or this flat part or this flat part, okay, and do whatever business I want to do on this particular surface. So of course we have studied spheres, cylinders, this cube also. But one thing which I would like to mention here is that of simplicity, just as I had a very nice representation for curve, I can have what is called as parametric representation of a, so surface. When I use the word surface, it is going to be in r feet. So is C2 or C1. Is it fine? I should say map. So sigma from AB cross right? So if you compare to what I have done for the curves, here I can write my surface in this particular form. I can take the domain as product of two intervals, and your image is sitting inside in R3. So of course you all have studied various ways to write down your equation of sphere, right? One of them is going to be what? X square plus y square plus z square is equal to 1. That is a sphere which is centered at origin and radius 1. But then there is spherical coordinates, right? R cos theta sine phi, R sine theta cos phi, and R sine theta R sine phi cos phi. Yeah? So if I write it in polar form or spherical form, so sphere, for example, is x, y, z, such that x square plus y square plus z square, this is unit sphere, or this is going to be cos theta sine phi, sine theta, sine phi, and cos phi. Okay, so of course these can be interchanged, where phi is going to be an angle from 0 to pi by 2, right? It is half, and the other one is going to be 0 to 2 pi. Here one is going to be pi. So you just figure out what is. So of course this is going to be a circle parallel to the xy plane, and so those are the latitudes, and phi's are going to be the vertical straight lines. Yeah, so those are going to be longitudes. So here when I write like this way, this is what is parametric form of your surface. This is what form is this?
Cartesian equation.
Yeah, Cartesian form, but if you remember, if you write it properly, it is going to be, if I write f x y z is equal to, so maybe I will go the other side rather than scribbling at the end. So if I define my function fx y z is equal to x square plus y square plus z square minus 1, then my sphere is
F inverse of 1.
f inverse of 0. F inverse of 0, right?
F inverse of 1.
No.
F inverse of 1.
If you put f inverse of 1, then you will have what? X, y, z is equal to 1. So x square plus y square plus z square minus 1 equal to 1. So it will become 2. It doesn't matter. Yeah. So yeah, I want that unit sphere. So I wrote f inverse of 0. So what one actually, if you will check among all the surfaces that you know, there are only two ways you have written it down. One of them is this parametric form, okay, where you are expressing your image as a function, three coordinate functions, as a function of two variables. Of course, that is why it is a surface, because basically you are thinking of it as depending only on two variables. Here, this is another way which we frequently write without realizing, but this is, you are representing your surface as a what? As a level set. Okay, so this is a level set. So actually, let me just mention any surface can always be written either in So rather than I do want to point out over here, parametric form, again, one keeps on thinking that it is a Cartesian form, but there is a better way to phrase it. This is can always be written either as a graph. Okay, so every surface either has a graphical representation or a level set representation, right? So if I draw something on the in 3 dimension, and if I want to think of it as a surface, either it is a level set or it is a graph. See here, when I am writing sigma st is equal to xst, yst, zst, what will I do? If I want to see what that surface is, I will put values of s and t and I will plot the points. So I am plotting a graph. This one is a level set representation. Okay, and of course, when I'm saying something is a surface, I also have to make sense of the fact that it is something like a plane, or just as we have seen over here, a curve, the tangent at every point is a linear approximation to your given function. So in the same way, if I am having a surface, so you look at this one, this representation over here. So I am having a square AB cross CD over here, and then what I'm doing, I'm having these coordinates S and T, and I'm plotting curves. So for suppose this is okay, so this is T direction and this is S direction. So if I fix T, then this is T fixed. So S going to sigma st, you will have these curves, and then I will have here T going to, these are going to be the curves where I fix the S variable and change the T variable. So the way I have drawn, of course it looks like a surface, and just as we have seen over there, for every point over here there is this tangent vector, which is a tangent vector to this curve as T is varying. There is a tangent vector to, for each fixed T you have as S is varying. So basically what is happening at each point on your surface, I have these two tangent vectors, and they are going to be, if they are linearly independent vectors, then they will span a plane which is called as a tangent plane. Okay, so one of the conditions for this particular object to be a surface, it can be just a constant map, right? Okay, that is a trivial surface, it doesn't move anywhere. So here, if I want to make a non-trivial surface, then the condition should be that these vectors. So how do I find this tangent vector in this direction? By differentiating with respect to S variable. If I differentiate with respect to T variable, I will get another tangent vector. So the condition should be that the gamma dash S, so S is a surface if sigma S and sigma T are linearly independent at each sigma st. Okay. And because we are in 3-dimensional space, it is slightly easier. Usually what one is interested in on any surface is that you want to create a frame of reference to be able to do measurement, to be able to do analysis on your object. Why, like physics or construction of engineers, they require, right, that they are not always working with a flat surface. So what you want is you want to create a frame of reference. For 3-dimension it is very easy because the cross product of these two vectors is going to be the normal vector to this particular surface. Okay. So basically what is the condition? The fact that these two are linearly independent is equivalent to saying that the cross product is not going to be 0. Right? It is going to be non-trivial at every point. Okay. So here. So this condition is equivalent to sigma s cross sigma t st. And if you look at that particular equation over there, if I write my surface as a level set, right? So what do you want to do? This is the parametric form. Yeah. If S is equal to F inverse of 0 or F inverse of C, then the condition is equivalent to for all p belongs to S. Okay, you have a well-defined normal vector at every point of your level set. Okay, for a constant map, for example, like I can have the inverse image to be a solid disk or a solid sphere, then it is not going to be a surface. Yes, what is the question? Did anyone asked? No. Okay, fine. So this was just some kind of basic introduction to how one thinks of as a surface or integral curve, and just to remind you about the existence and uniqueness theorem. Of course, like in the graphical representation, you usually write your surface as your S as graph over xy plane. You can write it as x, y, z, where z is equal to uxy. Okay, z is equal to uxy, and then again your condition is going to reduce to the same. The dot product of this vector. So here, in this particular case, it is easier to write it as fx, y, z is equal to uxy minus z. So your gradient of f is going to be ux, uy and minus 1. Okay, so these are various ways to make sense of surface. Now also I am not specifically mentioning mentioning the regularity. Okay, so you please just assume it is C1 or C2 as required. We are assuming enough regularity so that all these operation of derivative can be done. Okay, so just as we had ODE associated with our integral curves, what we are going to do is study the first order PDE in R3. We'll see a lot of methods in subsequent lectures tomorrow onwards to find solutions of the first order PDE. I just want to do slightly more of geometry here today so that one doesn't get lost in techniques and methods to solve PDA and realizes that one should also try to visualize what you are trying to solve. Okay, so let me see. So first order PDE is an equation of the form f of x, y, u. In some of the books it is written as z. P, q equal to 0, where p is equal to ux, q is equal to uy. So sometimes I will use this, or maybe the other teachers who are going to continue, Professor Shivaji will continue this first order PDE, so he may use the other notation. So I'm sure he will clarify whatever he will use, but just to make you all used to it. So or f of x, y, u, ux, uy equal to 0. So this is a first order PDE. It is said to be linear. If it is of the form, so it is said to be, let me write down. Linear if this is star is of the form okay, a of x, y, ux plus b of x, y, uy is equal to c of x, y. I think u does not appear over here. So the coefficients which appear over here are just function of x and y. This is the simplest case. I'm just for sake of the definitions, I'm just going through these particular terminologies. These are questions which one sometimes needs to answer for interviews, when you are looking for interviews. So this B is semi-linear if star is of the form ax, y, ux plus bx, y, uy equal to c of x, y, u. Quasi-linear if okay, right? So here the coefficients depend on x, y as well as the unknown variable, x, y, unknown variable, x, y, unknown variable. So in the second lecture that I will take, I will show the existence of solution to the quasi-linear equation. Okay, I will show the existence of this one. Now, of course, if your equation is in this form, it is non-linear. General non-linear first order PDE. So let us, still 10 minutes are there before I stop. So let me just motivate you this particular equation. Okay. So here I already have on the board this particular so first of all, the way I have written over here, ax, y, u. So my solution that I am going to look for is going to be what? It is going to be function of two variables from the solution. X, y can be considered as a surface. If I am given a function of two variable and if I plot it, it is going to give me some object in R3, right? Of course, I would be very happy if it is a surface so that no crisscrossing is happening. Okay, so considered as a z equal to ux, y. If I write it in this particular form, z is equal to ux, y. So over here, of course, I have written it as sigma st. I can just change this s and t to. So if I change my variable, though I will go back to my. So this is my x direction, this is y direction, and my surface is z equal to uxy. Then what do we know? The tangent. So the tangent vectors to the curves are going to be what? So I am writing my S is x, y, z such that z is equal to ux, y. So what are my tangent vectors? Yes? Yeah? Pardon? How will you visualize the points over here? Tell me. No. 1, yeah. So you see, it is just matter of writing it down, right? So you have here, you have x, y going to x, y, ux, y. This is going to be your parameterization. See? So this is the graphical form, your parameterization is this. So if I differentiate with respect to x variable, my tangent vector is going to be what? So this is, I should have some notation. So this is sigma. So sigma x is going to be 1, 0, du by dx. Sigma y is going to be 0, 1, du by dy, and sigma x cross sigma y is going to be du by dx, du by dy minus 1. This is going to be your normal vector, right? So now if you look at this normal vector, so let me call it n. You look at this particular equation. Yeah, I have axyu ux plus bxyu uy. If this cxy, I bring it on the left hand side, it becomes minus equal to 0. So maybe I should not do this here. Let me write it down. So your differential equation equal to 0, right? This is my first order differential equation. But what is this? What is this? In terms of this vector, it is dot product of A, B, C with n equal to 0, right? So so my differential equation is now written in this form. Okay, so what do I have to do? First of all, we need to remember we are on surface. Surface is uniquely determined by the normal vector, right? If I have a surface, it has those ux and uy, linearly independent tangent vector, which is whose cross product gives me a normal vector. Of course, it is going to be unique up to sign. There will be a positive vector and the negative vector. You can always choose to be one single normal vector. And my differential equation, first order differential equation, is saying the dot product of these two vectors is 0. What does it mean? What does it mean? Yeah, they are perpendicular. So what does it mean? It means that if I choose, so basically if this vector should lie along the tangent plane of my surface, I should find u such that when I take dot product with this particular u such that the normal of that particular surface is going to be orthogonal to these particular vectors, or these vectors lie along the tangent plane to the surface. That already reduces my problem from second order from R2 R2 to one dimension, right? Because now I only want to look for integral curves to this particular vector field. This is given to me, axyu, bxyu, cxyu. This is something which is given to me. I have to find u, of course, but I have one of the ways to solve it, or the way I can see to solve it, is to find a surface such that this vector is going to be along the tangent plane of the surface. That is what it is, and that is how we are going to solve the quasi-linear partial differential equation, by solving for integral curves to this direction vectors. The integral curves corresponding to these vectors are called as characteristic curves. Okay, so if you just think of it as a definition, then one forgets, but if you write your PDE in this form, then already you have an answer as to what you are looking for. You are looking for a surface, you are looking for something that is two-dimensional. So already it is coming with condition. Okay, now you want the normal vector to be non-zero. You don't want your ax, yu, bx, yu, zx or cx, yu to be identically 0. Otherwise you are not going to get anything. 0 dot any vector is going to be 0, so that is no condition. So when you think of it in this way, you also realize why certain conditions are put on your differential equations. Okay, you want differentiability, you want all the vectors to be non-zero, and what we are going to do in the next class is prove that locally we can find a solution to that particular PDE. The solution to the PDE is called as integral surface. Okay, we for first order for ODE we said integral curves. Here we are going to look for integral surface. So many times in the subsequent lectures, maybe tomorrow, you will see that they are called as, the solutions are called as integrals. Why? Because they are solutions to differential equation. Okay, so opposite of differentiation is integration, so they are called integral, but here we are going to say integral surface. Solution is going to be called or a characteristic surface. Some of the books also refer to them as characteristic surface. So maybe I stop here. It's fine. Yeah. It's 10 minutes break and I will restart on time. Maybe 10:45 I can start. Yeah. Thank you. So what I am going to show now is existence and uniqueness of solution of the first order this PD, the quasi-linear equation. And as I explained to you all, the solution to this particular ordinary, first order PDE or quasi-linear equation can be thought of as a surface, or we can look for a surface which is going to be a solution to this PDE. So surface is corresponding to, so there are some definitions. Surface is corresponding to of the original one, which can be any of this form. Are called as integral surfaces or okay. So by this I mean the plot of the solution uxy, z is equal to uxy, that will be a surface which is called as integral surface if u satisfies this particular differential equation. As I already explained, the PDE corresponds to the fact that the vector axyu, bxyu, cxyu lies in the tangent plane at every point on the surface. That is, the condition given by PDE is exactly that the vector axyu, bxyu and cxyu lies in the tangent plane. And yeah, so the vector field, so let me just write down field x, y, z going to ax, y, z, b, x, y, z, c, x, y, z gives characteristic direction and the integral curve of this vector field is called as characteristic curve. So what does it mean? What does it mean? I have a vector field in R3. Okay, I have a vector field in R3 x, y, z map, which is going to x, y, z, going to ax, y, z, bx, y, z, cx, y, z. And for this particular vector field, if I find an integral curve, it is going to be called as characteristic curves. So you remember that when I drew the surface, my condition is that I want this particular vector field. So this is A, B, C is given. I want this particular vector field to lie in the tangent plane at each point, right? So the best way is that if I think of it as a vector field, I can try to find a curve which fits this vector field. That is just initial value problem of ordinary differential equation, for which I know existence as well as local uniqueness, right? So for each x naught, y naught, for each x naught, y naught, z naught, initial point, and given some relation, I can always find a curve which passes through this point. But this gives me only a curve. I am looking for a surface. So how does one get a surface? I have already shown. I need two directions which are independent, right? So what should I do? I have some initial value over here. So instead of, if I start from one point, I will get only one curve. But if I start from several points, I will get several curves, right? So I will have something over here also, something over here also, something over here also. So ideally, I should start from something which is an initial curve. Okay, I should start with initial curve. So if it is like I want to cover something as a surface. If I have a point, I can give one curve. But if this curve is nice, I can have not parallel but kind of curves which will start over here. They should not intersect each other, otherwise the surface is going to twist and all that. So locally your basic existence and uniqueness guarantees that for each point over here there is going to be a curve. Okay, and then what should happen? When I combine all these curves, I should get a surface which is an integral surface, in the sense that it should satisfy that particular property. Okay, so most of the time what you are going to do is you are going to start with something in parametric form. It is very easy to write a gamma s. I have given gamma s. You take a point over there, then you find a curve. That's all that I am going to do. And then later on, I want to find a condition which ensures that it is a surface. If it is a surface, then it is going to be an integral surface because I constructed the curves satisfying the condition I require. You understand what I am trying to say? It is all related to your ODE, existence and uniqueness theorem. For each initial point, I have a curve. I will combine that curve and I will say it is a surface. Of course, arbitrary union of curves is never going to be a surface. So there will be conditions. Once those conditions are satisfied, we will see that it is going to be an integral surface because I constructed my curves to be characteristic curves. If I start with characteristic curve, it is already satisfying the condition that the derivative, the tangent to the curve is this particular vector. So that normal dot this vector is going to be 0. So checking it is an integral surface is going to be easy. To obtain the surface requires some technicality. It is not difficult. It is just your implicit function theorem which will give you the result. Okay. So I will give statements and also try to explain the proof. But in your thoughts, you just keep these ideas which I have explained to you all, okay, and not get lost in the notations. Okay, so let me write down. So here I have already described. This is a vector field characteristic curve. How do I describe the characteristic curve? So the characteristic curves is solution to ODE. What? Your first derivative dx by dt is axyz, dy by dt is bxyz, and dz by dt is equal to xyz. This is what I said, right? It is a integral curve corresponding to that particular vector field. Okay. So these are called as so if I give you an initial point, I can always solve this particular system of ODE. Basic existence and uniqueness theorem will say that there exists unique solution to this particular system. I will get only one curve. Okay, for whatever point I choose, I will get a curve. That is what will happen. Okay. Basic existence and uniqueness theorem of ODE implies curve near the given initial value in initial value. Just let me stop over there. Initial value. So I will call it as x naught, y naught, z naught. Okay. So if I give you x naught, y naught, z naught, I have a unique curve or in neighborhood of that point. Okay. So let us formally prove results. Okay, because it is not just motivation and discussion. So let me prove. Let S be an integral surface given by Z is equal to uxy. No, sorry. It's not a degree of surface, sorry. Yes, the union of characteristic curve solving. So I will call this as 2 star. Then S is an integral surface of the PD. Okay. So, do you understand what is the statement of the theorem? Or is there a confusion? Tell me. So, it is exactly what we expect. Okay. What we are saying, if I have a surface which is given by z is equal to uxy. Okay. When I am saying S is a surface which is given by z equal to uxy, which is collection of characteristic curves, it already means that it has a well-defined normal vector, it is C1, etc., etc. So it is a surface which, so if I collect the characteristic curves, then I already have a surface. Okay. I want to say it is an integral surface. What does it mean to say it is an integral surface? To show that it is an integral surface, I have to verify that at every point on the surface, this particular differential equation is satisfied. That is all. Okay. It is just to get your thought process in line. Okay, because it is like you just now said this and you are proving the same thing. No, I said it because that is how we are going to solve the problem. But this is actually verifying what we said or what we expect to be true. So that is what mathematics does sometimes, right? You have to formally also write a proof. It is, you started like that, but you also have to prove it. Okay, so what does it mean? You want to show it is a surface. So what do you want to show? You want to prove that S is a integral surface, means that you satisfies this particular equation. So you have to prove that S is an integral surface, that is for any P belongs to S, the following equation is satisfied. Okay. So, as I usually tell my students, mathematics is not just solving problem. You have to convince people your ideas, right? You have to explain to them what you are saying is according to the definition, right? And it is like, it is not just intuition, it is actually what we want to show. Okay, so there is a proof over here. So what do I need to show? It is an integral surface. You let P belongs to this one. So we write P equal to x naught, y naught, z naught belongs to S. Because it is a point on S, we have u of x naught, y naught is equal to z naught. I want to say that this relation is satisfied at P. So when I put x naught, y naught, z naught, this equality should hold. Okay. So now, because P belongs to S and S is union of characteristic curves. So there exist unique, right? I said there exists unique characteristic curve. So usually when we say that curve is passing through P, I will write it gamma P of 0 is P. Okay. because it is a characteristic curve, it satisfies the differential equation, right? So also x prime t is equal to a, y prime t is equal to b, and z prime t is equal to c, right? Yeah. Now consider so this A, B, C lies in the tangent planes to S, right? That is the definition of tangent vector. You have a curve, the tangent to it is going to be a vector in the tangent plane, right, to that surface. Okay, so now because your ux uy minus 1 is normal to S at and this is a tangent vector, dot product should be equal to 0, right? So you have A times ux plus B times uy minus C is equal to 0. Satisfied. Okay? You follow what I have done? Yeah. The thing is, this comes from the theory of surfaces actually. So what happens if I am having any surface? How do I find a tangent vector? I will have to take a curve inside the surface. The tangent to the curve lies in the tangent plane to the surface at that point. So this is true in general, right? So again, this comes from geometry. I started with the parametric representation ux and uy, and the linear they are linearly independent. So I have a tangent plane, but you know that if I have a point and I have a tangent plane, there are infinitely many vectors, right? They are all written as linear combination of these two things, but there are other vectors also, right? So how do I find those vectors? Every tangent vector can be found as a tangent to a curve which lies on the surface. So that is how one should, so one can define a tangent plane to the surface as equal to collection of all vectors which can be identified as a tangent vector to some curve on the surface. I don't care if there is a curve. So if I take a curve like this way, which is on the surface, every tangent to this curve is going to lie in the tangent plane. Okay? If there is some curve which goes out of the surface, it's of no use. As far as it is here, it matters to me, right? Once it goes outside, it is a space curve. It has nothing to do with the surface. So if I want to do analysis on the surface, I only care about what is happening here. I don't care what is happening here. Anything can happen, but I am doing my analysis here. So if I am thinking of a tangent vector or a vector in a tangent plane to this point, the only way I can think of is by looking at some curve. So this is a way of seeing how I get my tangent vectors. Okay. So if you do special cases like surface, the spheres or cylinders, if you do it in your class, then you can explicitly see what it is. Okay. So this was very simple. What it says is, if I have a surface which is collection of characteristic curves, union of characteristic curves. So when I say something is a surface, already normal, proper normal exists, etc. So then this is trivial. Okay. Converse is also true. Every integral surface is union of characteristic curves. Okay. Then next I will show it exists. I can find a solution, nice solution to the integral curve. So, see. So many times, as a student, one thinks that what are we proving? Means this is so obvious. You started with this and you proved this. No, we started with intuition. We started with a surface which has certain properties. Then we showed it is the required solution. And conversely, every integral surface can be obtained as a union of characteristic curves. Okay, so so I will write it down. Yeah. So. So here, what I am saying, I am using the same notations which I have already written here. Okay. So here, what I am trying to say. Okay. Again, I am not showing existence as yet. I am only saying the following, that if I have an integral surface, means if the solution to the partial differential equation exists, u, x, y exist, then if I draw the graph, z is equal to u, x, y. That is what is my definition of integral surface. Okay. Then that particular object is going to be union of characteristic curves. Okay. Firstly, union of characteristic curves. If a surface is union of characteristic curves, then it is an integral surface. Conversely, if I have an integral surface, means the solution u exists, then every through every point I will have a characteristic curve, and S is going to be union of characteristic curves. Okay. So what do we have to show over here? Here I have not, again I am not specifying for all t where. Okay. Actually it is for all t for which the solution to this particular system exists. Okay. There are unique characteristic curve. So this solution to this will exist depending on your initial point. So for whatever t your solution exists, that curve should lie in S. It cannot go out. That I drew something right over there, it is going out. I started over here and it went out. What this theorem says, that if this is an integral, if this is a characteristic curve, if I start over here, I have to remain over here. I cannot get out of that particular surface, and hence it is union of characteristic curves. Okay, here, take your time afterwards to go through what has been done in the class. I mean, it seems like, you know, again, it is too easy, right? Means we just started, we are just applying definition, but it means a lot about how we can construct a solution. Okay? So, let me start. Maybe, yeah. So here I have already fixed the notation that gamma of P of t is equal to xt, yt, zt is the integer curve through P, say defined for P belongs to T naught minus delta, T naught plus delta. Okay. Where gamma of P of T naught is equal to gamma of 0 is P. This is 0 minus delta from 0. Delta greater than 0. Okay. Now what do I have to show? How do I check that this curve lies on my surface? Z equal to uxy? Yes? How do I verify that this curve lies on the surface Z equal to uxy? Which is yes? How do I show that this curve lies on the surface Z equal to uxy? No. I am already having, see that is the, that already is, this is a curve which is having ABC as a tangent vector, right? Now, I want to say this curve lies on the surface Z equal to uxy. It should satisfy zt equal to u of xt yt. You follow? So, that is how I have to, so once I say that all these points which lie on the curve satisfy that equation, then my curve is lying on that surface. You follow? So earlier the curve was on surface. Okay. Here I want to show that if it satisfies this condition, it lies on the surface. Okay. So the trick is again the proofs are usually very easy, but once one understand what we have to do, right? So what do I want to prove that gamma p t belongs to S for all t belong to, this is what I want to show. Okay, that is to prove that zt is equal to u of xt yt for all t belongs to. Okay, so we will be very smart. Define ft to be equal to right? Yeah, I will give you time to write later. Okay, just pay attention. ft equal to xt yt. I want to show this equality. So it is same to prove that ft equal to 0 for all t belongs to minus delta delta. That's what I have to show. Now you see, this is just a curve. I will use basic existence and uniqueness theorem nicely without doing any effort. My f of 0 is z0 minus u of x of 0 y of 0, which is z0 minus u of x0 y0, which is z0 minus z0, which is 0, because I had started with P is a point on the surface, right? Okay. Now f dash t differential equation क्या है? It is going to be minus, it will be du by dx x dash t minus this is what? This is going to be what? No. What happens to this equation? Here? So, we actually want to show that this whole thing is 0, right? So, I want to say that f dash t is 0, but I want to prove that. I do not know that. I only know f dash at t naught is 0. Again, why? Because it is a point on the surface. Only P is a point on the surface. So at that particular point, I know the normal vector is given by that A, B, C. So the dot product at that particular point is going to be 0. समझ में आया? Agreed? Yes? So what? We have found f which satisfies the condition f of 0 is 0. So this is, f dash of 0 is 0, which is a solution to this particular differential equation, right? By basic existence and uniqueness theorem, only identically 0 function is a solution of such equation. 0 is the only function whose initial value will be 0 and the derivative will also be 0. Okay? So by f is identically 0. Okay, but that is what we wanted to prove. So this curve lies completely in S. Is it fine? Is it fine? Yes? Yeah? So you have to differentiate and then evaluate it at origin and use the fact that the tangent vector, the point P is on the surface. Okay, and A, B, C at that particular point are going to be the tangent, it lie in the tangent plane because it is an integral surface. Is this fine? Any doubts? Or it came like a magic, right? Right? You check everything at one point and you get the whole result for the whole curve. Yes? So if you have doubts, you can ask me later. Okay? So this is what we have proved. Every surface which is going to be an integral surface is union of characters. So if and only if result we have proved. Next I will just do the existence result. Okay? So here it also means that if I have two integral surfaces and if they touch each other, then they have to touch along the characteristic curve through that point. Because the characteristic curve lies completely, other one also characteristic curve has to lie completely, as long as it is an integral surface. Again, tomorrow you will see when you are solving general solution of this first order PDE, you may see the solutions as intersection of two surfaces. When two surfaces intersect, they intersect along a curve. So there are methods where you obtain the solution as a intersection of two surfaces. Okay, so characteristic surfaces, intersection of two surfaces. Okay, so let me prove. Still time, right? How much time I have? 15 minutes. 15 minutes. So, solving the partial differential equation is usually phrased as a Cauchy problem. The Cauchy problem for the quasi-linear equation. So, I am not going to write again. Is to find an integral surface passing through Okay, so this is what is going to be called as a Cauchy problem. So you will see Cauchy problem for other equations also. So usually it is referred to as initial value problem in the ODE case, but here we will call it as Cauchy problem. So here, so we assume that the functions A, B, C, F, G, H, B, C1 in neighborhood of point P, which is given by Fs. Now, so again, not to get lost in this whole literature, let us go back to what we have, what we are trying to do. So as I said over here, when I had drawn this figure, ideally, because I have proved every solution is going to be union of characteristic curves. Finding characteristic curves is easy because I am only solving this, right? So majority of work is already done. The only problem is the following. Okay, if I give you point here, you will find a characteristic curve. Okay, but suppose that curve gamma is such that gamma s also corresponds to this curve itself. Okay, then if I choose any initial point over there, I'm never going to get out of that curve. I'm not going to get a surface. You follow? I will not get a surface. If my initial curve is such that it already satisfies my differential equation. What I am saying, if it is already of this form, then if I solve my ODE, I am never going to get out of this curve. Okay, so then it is not giving me a surface. It is just giving me same curve. Whatever I try, 100 times I may try, I will not get out of that curve. So that is where the condition comes that I want my curve gamma s to be something like this. So that whenever I choose my initial point over here, I will get something nice which will allow me to create a surface in neighborhood of that particular point. So that is all that I am going to write now. Okay, idea is same. Solve for the characteristic curves, and so for each point over here I will have a characteristic curve where the initial value, see here I did not write the initial value. So my initial value will depend on S. As I move S, I will get a collection of curves, and then when I put all of them together, it should be a surface in the sense that normal and all those things should be well defined. That's all, nothing else. Okay? So I will quickly write down. So for each S, so here let my S belongs to AB. For each S, so not only that, where is P? I write P. I have written here. So for each S belonging to S naught minus epsilon, S naught plus epsilon, see this, or I will write on the characteristic curve. So through the point, which one? Okay, that is what I am going to do. Okay, so S naught, this point is over here, my S naught is over here, this is my point P, this is gamma of S naught. Okay, and for every S, there is these points, I am going to find a characteristic curve. Characteristic curve means it satisfies this particular equation. Already your AB is in this picture. Okay. Yeah, so that is sigma of S0, which is X S0, Y S0, Z S0, which is equal to what? It is going to be equal to Fs, Gs, Hs. Okay, that is what we have. Yeah. So in fact, I already have my two parameter family of curves. We have I also want to say that I should be able to extract integral surface from this parametric representation of the surface, right? So what do I mean? This I have solved using this system of equation and basic existence and uniqueness theorem. If I want to say that this is an integral surface, I need to find u. How do I get u? I will get u if I am able to represent this parametric expression as a graph. Yeah. So if I have xst, yst, zst, and I want the last one to be written as z is equal to ux, y. How do I do it? Yes? Yeah, but how do I get from parametric representation to graphical representation? You get it by implicit function here. Okay? So you are having f, capital F, which is a function from interval. Here there are two intervals. I have s0 minus s0 minus delta to s0 plus delta. So if I define, so this sigma is defined from where to where? It is s0 minus delta, s0 plus delta times some epsilon to epsilon. It requires more work because I am saying that my epsilons are not depending on my initial point. So you are using the conditions of existence and uniqueness theorem to say all these independence. But here when I am writing like this, this is a parametric representation of a surface. It will be an integral surface if I am able to write it down as a graph on xy plane. You see, like if I have 3-dimensional figure over here, and if I have something like this way, this part cannot be written as a graph over xy plane. You require a condition, and that condition is given by the implicit function theorem, right? So which is possible. Implicit function theorem. If, so this is your condition. Determinant of this particular quantity evaluated at the point P is not equal to 0. Then in neighborhood of point P, you can write it as a graph. You can write your z variable in terms of x and y variable. Okay? Yes? So this is the proof of existence and uniqueness of your solution of quasi-linear equation. Yes? So this is why the condition comes. Okay? So finding solution of characteristic curves, collecting all the characteristic curves, And to say it is a surface, you have to verify the condition of implicit function theorem in neighborhood of the point which you are interested. Remember, most of the time we are solving only in neighborhood of a point. We are doing things locally. Okay? As one of the participants says, locally it is like a plane. Locally it is a surface, can be locally written as an image of a neighborhood in R2. So I think this completes the quasi-linear proof of existence of solution of quasi-linear equation. I will stop here. Huh? 15 minutes break? Okay. So we'll have 15 minutes break to clear the board here. Yeah, here. Fine. And the next speaker will be Professor Kulkarni, will be taking the class. Okay, fine. Thank you.
On behalf of all the participants, I like to thank Dr. Jyotshana Prajapat for such a nice session. And the best thing was she started from the scratch so that we all could brush up whatever was forgotten. And the next session after 15 minutes will be by Dr. Kulkarni. Thank you.